Okay, it is just past the hour. We're going to get started here. My name is Ian Campbell. I'm the Vice President of Operations at PACICC, and I am the staff lead for the Risk Officers Forum, and I'm your host for this afternoon's broadcast. So welcome, everybody. Special welcome to first-timers that are joining us. This is our second webinar, Emerging Risks webinar of the year. Today, we're looking at climate change modeling. And I want to thank my colleague, Dipika Deol. She's going to be working behind the scenes to field your questions and comments as we go throughout the broadcast. So encourage you to relax and enjoy the next 90 minutes of discussion. Danica has posted there the agenda for today, so I'm going to quickly review some housekeeping items, and then I'm going to introduce our panel and hand off to the panel. And then I'll rejoin the broadcast to close, talking about the remaining events in 2022 and the follow-up satisfaction survey that you're going to receive. So you are very familiar with this, the Microsoft Teams platform that we do invite your questions and comments in real time throughout the broadcast. So use that finger, as we go through this, or the chat box to field to submit your questions or comments. We will get to them in real time throughout the broadcast. Reminder that the Antitrust Act, the Competition Act is in place. Antitrust compliance. You are competitors and remain competitors throughout the broadcast, and that satisfies our lawyers, so we're good there. The meeting is being recorded. You're going to see a copy of this on our website for anyone that is not able to join us and wants to tune in later on. You can do that. You're going to see 3 different slide decks today, and I will have copies of that available, and we'll send those to members following the broadcast. So let's get to our panel. It's always good when you have a tough subject to bring in an expert moderator. So we have Glenn McGillivray, Managing Director for the Institute for Catastrophic Loss Reduction. A longtime friend. Thank you, Glenn, for being on the broadcast. Glenn moonlights as an adjunct professor in the graduate program, Disaster and Emergency Management at York University. So welcome, Glenn. We also have Rachel White, Assistant Professor, Department of Earth, Ocean and Atmospheric Sciences at the University of British Columbia. She's going to be our first speaker. Second speaker is Dipika Deol, Head P&C Treaty Underwriting, Canada and the English Caribbean, and also Senior Vice President of Property and Specialty Underwriting with Swiss Re. And our third speaker, last but not least, is Mathieu Boudreault, Professor of Actuarial Science in the Mathematics Department at the Université de Québec à Montréal. So welcome, Mathieu. And I'm going to now hand off to Glenn, because the more I talk, the less time I have for our expert panelists to discuss the subject matter. So over to you, Glenn, with our thanks, and lead on.
Thanks, Ian, and thank you, everybody. Thanks for joining us today. It looks like a good group. We're going to spend the next hour and a half or so talking about climate change and climate change modeling in particular. Our speakers have already been introduced to you, so I'm not going to do that again. But I'm going to flip it right over to Rachel to start off. I'll hand over to Ether to her. And then we'll get on with the Dipika after that. So Rachel.
Great, thanks, Glenn. Can you hear me and see my slides?
Yep, absolutely.
Okay, great, thanks. So yes, my name's Rachel. I'm an assistant professor in climate dynamics here at the University of British Columbia. I do want to acknowledge before I start that the University of British Columbia is situated on the traditional, unceded and ancestral territory of the Musqueam people, and I am honoured to be on lands that they have tended and cared for time immemorial. So I'm a professor in climate dynamics, so my expertise is really in the climate models. I use and I run climate models, and I look into what they can tell us about how extreme events are going to change into the future. And so I'm just going to give you a sort of a broad overview of some of the things that climate models can tell us, and things that they can't tell us, and things that we need to be on the lookout for in terms of extreme weather. And so I do have a quick overview here. So we're first going to look into some of the extremes that I'm going to talk about, including extreme heat and extreme precipitation. And so those aren't necessarily the ones that cause the most damage in terms of the insurance industry, but from the physics and the climate perspective, those are the ones that we sort of have the most certainty about what the changes are going to be. And so the further down that line we get towards the actual costs, the harder it is and the more uncertainties come into play. And I think Dipika and Mathieu will talk a bit more about those aspects. So I'm going to start off with that and move on to talk about global climate models, a very brief introduction of what they are, what they can tell us. I really want to focus a bit on the power of ensemble modeling and the role of internal variability and how these climate model ensembles can really help us understand internal climate variability and force trends. And I'll talk a little bit about aerosols versus greenhouse gases, some of the limitations of global climate models, particularly focusing on the resolution and downscaling and what sort of options we have for that, and tie that back into the internal variability in that question that we have of, okay, and this ensembles and how we get ensembles of downscaled models. So just sort of starting really broad overview, expected changes in mean temperatures and just getting everyone sort of on the same page. I'm going to be talking about these RCPs, these representative concentration pathways. These were the sort of agreed upon scenarios for how greenhouse gases, not just carbon dioxide, are going to change into the future and sort of variety of different futures that we might have. These came out from the Intergovernmental Panel on Climate Change 5th assessment report. And so this was about sort of 6 years ago now. The latest report that came out last year actually uses these shared socioeconomic pathways, or SSPs, in combination with the RCPs. And so the RCPs are really telling us about the greenhouse gas concentrations. The SSPs are telling us about how we got there and sort of what the world looks like to have got to those greenhouse gas concentrations. And so acknowledging that there are different pathways we could have taken. And all of those different pathways affect adaptation ability and mitigation as well. But I'm really just going to focus on these RCPs because they're the ones that affect the greenhouse gas concentrations, which impacts how much warming we get. And so these are just a couple of figures from the 2019 Canada's Changing Climate Report of changing temperatures in winter on the left and summer on the right. And so the red line is for RCP 8.5. And so this sort of business as usual, it's often called. And so we do very little to mitigate climate change. And then the blue line there is RCP 2.6, where we do a lot to mitigate and reduce the greenhouse gas. And so moving on to sort of, okay, we have these increases in temperatures. This is global warming, but the impacts of carbon dioxide and these greenhouse gases on the atmosphere is to warm the atmosphere. But the thing that we're interested in is not sort of, well, how much do the average temperatures warm by? Those aren't the things that really impact us. What impacts us are the extremes. And so then the question is, well, how do we link these these changes in the average temperature to changes in extremes? And so here we have a graph looking at increases in annual maximum temperatures. And so on the y-axis here, we have the recurrence time or the return period. So going from 50 here in the red, we're starting, so this is a 1 in 50 year event in the sort of 1986 to 2005 climate. The green is a 1 in 20 year event and the blue is a 1 in 10 year event. And so you can see that as we go out into the future, the frequency of these is going to increase. And so that's because we've got this increase in overall temperatures causing an increase in these heat waves. It also means we'll get a reduced intensity and reduced frequency of cold waves if we just look at this shift in the mean temperature. And connecting this back to some of the extremes that really have large impacts, for example, wildfires. So we know that there's sort of 3 conditions for wildfires: hot temperatures, dry fuel and dry conditions, and high winds. And so with these increasing temperatures, we're obviously increasing the probability of wildfires from the temperature perspective. We're also likely increasing the probability from the evaporation, from the dryness perspective. By having the atmosphere and air be warmer, we can evaporate more moisture from the fuel, from the vegetation. And so that can also lead to an increased probability of wildfires. There is a question mark on that because we do expect some precipitation changes through climate change, and those are more uncertain. And we don't really have a good sense of how winds are likely to change. And so that's sort of a bit of a uncertainty on this, how we connect these average temperature changes to changes in wildfires. And so I think it's important to sort of understand, well, right, why are we expecting changes in extreme heat? And for me, it's interesting that there's two aspects of this. And so these graphs sort of show that quite nicely, that we have this distribution of temperatures. And so we've got sort of this old climate, and we're shifting this entire distribution of temperatures towards the right with global warming, which means we're getting more hot weather and more record hot weather that we've never seen before. And so this is sort of the well understood impact of climate change. And then there's another impact potentially of climate change. And so essentially to do with how the world is heating up. And so it's not the case that everywhere on Earth is heating up at exactly the same rate. We do have more warming in the polar regions known as Arctic amplification. Land is heating quicker than ocean because of the ability of the differences in heat capacity in land and water. And so those can influence atmospheric circulation. And so this idea is, well, actually, we might be changing the variability of the climate as we make these changes to the mean temperature distributions. But I will caution that this is really an area of active research. This is one of the areas that I research, and there's no real consensus in the scientific community about whether this is really likely to happen. And that's because we don't have enough observations yet, because of the internal variability or natural variability in the climate, and because models don't always agree. And so we'll get a bit more onto that in the later half of the talk. So that's sort of looking at extreme heat. We can also look at the same for changes in extreme precipitation. And so here we have that same graph. And so we're looking at this 1 in 50-year event, 1 in 20, 1 in 10-year event. And again, looking out into the future, we can see that all of these are becoming more common or more frequent with global warming and these increases in temperatures. And so as we get these increasing temperatures, we do get increasing extreme precipitation. And this does include increase in extreme snowfall if it's cold enough. And so the sort of physical background behind this is the same for both snow and rain, but it's also the case that in regions where you're close to that freezing line, you're also warming temperatures. And so you're going to get a shift from snow to rain. But if you're somewhere where it's minus 30, when you increase that by 2, 3, even 4 degrees, and now it's minus 26, it's still going to snow instead of be rainfall. And obviously this can lead to increased flooding. And there's a couple of examples just from recent years, Manitoba floods sort of very recently, and BC floods back in November, more based on where I'm based in BC. And so thinking about why we're expecting this, again, there's a very sort of simple physical explanation that if you have warmer air and you have warmer surface temperatures of water, so the ocean and lakes, you're going to get more evaporation. So we're going to put more water vapor into the air. And when we're looking at extreme precipitation, we're essentially saying that extreme precipitation does seem to scale with how much water vapor there is in the air. That isn't an argument we can always do with mean precipitation, and so there's a lot of sort of discussion about there are some regions that might be getting drier, but the extreme precipitation might also be getting more intense. And so we can follow sort of some basic physics laws and say that as we increase the air temperatures, the ocean temperatures by 1 Celsius, we're expecting that the amount of water vapor in the air to increase by about 7%. And so we could say that maybe this is what we expect extreme precipitation to do. However, there's a number of sort of interesting studies that suggest that actually it might go as sort of super Clausius-Clapeyron up to maybe 14% per 1 Celsius warming. And again, this goes back to some of the dynamics that we've got this thermodynamic part of it where we're increasing water vapor by 7%. But there's also a lot of dynamics that go on in these extreme precipitation events. And so to do with the convection and how that is enhanced by the enhanced water vapor. And there's some evidence from some observations around the world that actually we might see this super Clausius-Clapeyron. And so sort of as a bit of a summary, like thinking about, well, what we really need to know is how much are these extremes going to change? And so I sort of split this up into sort of 3 here. So we've got our physical understanding of actually, looking at what we know about the physics and understanding how that's going to change. And so that's sort of telling us that heat extremes, if we're just looking at the thermodynamics, will change linearly with mean temperatures. And so we can use extreme value theory and just sort of shift those by a mean temperature to see the changes in these return periods. And minimums are expected to change more than maximums, and there's some sort of fairly well understood physics behind that as well, in terms of what causes hotter temperatures and what causes the colder temperatures, and how much role solar radiation plays versus long wave forcing, which is more affected by these greenhouse gases. And then we have precipitation extremes. As I said, Clausius-Clapeyron suggests 7% per degree C of warming, but there are suggestions that maybe there's some dynamics at play that could produce more than that. But we can also look at observations so far, and so look at, well, how have things changed? And the problem is that for extremes, we don't really have enough data if we're really looking at the really biggest extremes. And so if we're wanting to know, how much does a 1 in 20 or a 1 in 50 year event change with climate change, we need to have had, I don't know, I'd say at least 10 or so 1 in 50 year events. And so we'd have to have a lot more observational data than we currently have. And so we can sort of build these models. And so here's a figure from, again, this Canada's Changing Climate Report, looking at changes in the highest daily maximum on the left and the lowest daily minimum on the right. And so you can see that particularly for minimum temperatures, they have been increasing over this time period from 1948 to 2016. We've seen a smaller change in the daily maximums. As I said, this is sort of expected because of the physics. And even actually, there are some regions that show this decrease in the daily maximums that I might have time to get onto later. And then the third thing we can use is these numerical climate models or global climate models. And we really have the most confidence in what's going to happen in the future when all three of these agree. And so there are some things that we have much more agreement on than others. And so moving on to global climate models, I do just want to give a brief overview. I don't know how much you all know about this, so apologies if this is going over something you all already know. But these climate models are essentially a way of splitting up the entire climate system. And so that includes the atmosphere, it includes the ocean, it includes sea ice, it includes land ice, it includes sort of land and different land use types. And essentially we split the entire atmosphere into these cubes, and then we solve physical equations. And so we sort of say, well, if we know what the temperature in this cube is, we know what the wind speed in this cube is, then we know that it's advecting temperature with the wind. And so we know how that's going to change the cube next to it. And so essentially we're solving all of these grid boxes across the world for temperature, for humidity, for wind speed, for pressure, for all of these factors. And so we've got a lot of physical processes in these, and we're trying to estimate clouds and rainfall and radiation, and how the clouds are impacting the radiation, and how that then affects the temperature profile, and how that is going to impact convection, which is going to impact clouds. And so all of these processes we're trying to sort of model within this global climate model. But as you can sort of see, this is a bit of a not necessarily an exact representation in terms of the grid box size, but when we're thinking about global climate models, the grid boxes are fairly large. And so if we're looking outside and thinking, well, what's the scale of a cloud? Our grid boxes are not the scale of single clouds. They're the scale of sort of 100 kilometers or so. And so we really do have to come up with estimates for a lot of these processes within the model. But essentially, we can take this model, and we've got a model that now represents the climate, and we can force it. And so we can add in these greenhouse gas forcings, these RCP scenarios, and see, well, how much will the temperature increase? And so that's what they're very good at sort of giving us an estimate on, is this sort of idea of climate sensitivity. And so if we double carbon dioxide, for example, how much will the temperature increase? And so the other thing we can sort of dig into is whether there are competing factors. And so we've got an anthropogenic increase in aerosols over the last century, as well as an anthropogenic increase in greenhouse gases. And this paper was looking at the change in atmospheric rivers. And so the red color is showing a decrease in the atmospheric rivers, and a blue color is showing an increase. And so what we're actually seeing is that the aerosols and the greenhouse gases have had competing impacts on both atmospheric rivers, and here we have on hottest days as well. And so we've got a decrease in hottest days because of aerosols, an increase because of the greenhouse gases, and then the total is actually quite mild. And so if we're reducing aerosols, which we tend to be, and don't reduce our greenhouse gases, it's likely that what we've been seeing up to now with the warming will actually be stronger into the future. And so this is where the models provide a benefit over the observations, because it allows us to see how this might change as we do things differently into the future. And I realize I'm getting quite close on time, but the one thing I really want to cover is this role of uncertainty and this idea of this emission scenario. So we've got these different RCP scenarios that look at different futures and how important that is for different timescales. And so this is a figure looking at global temperature change and essentially trying to estimate where the uncertainty in our answer comes from at different lead times. And so as we go out into the future, the emissions scenario, this green bit, becomes much more important. And so if we're looking at what the climate is going to be like 100 years into the future, then yes, the emissions scenario really matters. But if we're looking at what's the climate going to be like sort of 20 or 30 years into the future, then the emission scenario is actually less important than sort of model uncertainty or internal variability. And this one is for global climate change. And if we take a regional climate change, this is an example for the British Isles, there was an example for Canada, unfortunately. But you see that when the emission scenario becomes important, it gets later and later. And so that's sort of one of the key messages that I wanted to bring into this talk, is that when we're thinking about changes in the next sort of 20 to 30 years, the emission scenario is probably much less important than this internal variability and model uncertainty. And so running one model is not enough to get a good sense of what might actually happen. And so I'll just go through this one figure where, because I just quite like this, there's a nice paper that looks at what we could have seen over this 1966 to 2015 time period. And so here we have the observed temperature trend over this time period. But this one on the figure next to it is sort of an ensemble mean. So we run a lot of different climate models with the same forcing and see how they all change. And they're all going to change in different ways because the climate has this natural variability. Some years are hotter and colder than other years. And so this ensemble mean gives us a good idea of, well, this is the actual, like the forced response to the greenhouse gases. But then they sort of applied the variability to this ensemble mean and produced all these different ensemble members, which are essentially equally plausible versions of this top left figure that we could have seen over this time period because of the internal variability. And so perhaps I will finish on this slide. I had a couple more to go through, but I am running out of time and I want to leave time for the other speakers. All models are wrong. And so I think that's one thing we need to keep in mind. That's also true for climate models. They're making a lot of assumptions and they do have biases. And this statement is attributed to statistician George Box. I don't know whether he actually said it, but some are useful. And so really understanding what those limitations are, I think is critical. And so I'll just skip forward to this one where I was mentioning that these climate models, these global climate models are at these spatial resolutions where a grid box is sort of 100 kilometers across, which isn't very useful when we're really trying to understand impacts on the ground. But we also have this problem of this internal variability, that if you run one climate model, it'll tell you a plausible future. But there's so much natural variability in there, particularly when we're looking over shorter timescales, that if you ran it again with just a slightly different initial condition that's equally likely, you might get a very different response. And so it's really key to be running these ensemble forecasts or ensemble climate models, so you do get a sense of what's the most likely response and what's the range of possible responses because of the internal variability. If you just run one model, one simulation, it'll give you an answer, but you don't know whether that's actually the forced response to greenhouse gases or just part of the natural variability. And so this was a really nice project where they were trying to look at extremes, and they had 50 member ensembles. And so they started with a climate model and then downscaled to much smaller resolution and got all of these ensemble members. And so just to give you a sense, this is showing the short-term climate change projections for mean December precipitation, and each one of these is a different ensemble member. And so you can see they all come up with very different answers. And so all of these are equally plausible changes in precipitation for this short term. So this was 2020 to 2039 relative to 2000 to 2019. And so we do need to take care in making sure that we're sampling this natural variability and not just, for example, running this first one and saying, okay, it's going to have a decrease here and an increase here. And so I will leave my conclusions up. I thank you for your time. And if I have any time for questions, I'm happy to take some, or I think maybe we need to move on to the next speaker.
All right, there is actually one question in the chat, and it is there an expected increase in severe convection storms such as hail?
Yeah, that's a really great question and something that we're the research community is actively working on. But the problem is for storms like that, there's so much small scale processes that really matter that it's hard to know what this sort of large scale increase in temperatures is going to do. And so there is some evidence that we might get these more intense, like if you have more warmer temperatures, for example, with tropical cyclones, when the sea surface temperatures are warmer, you can get more energy into those systems, and so they can become more intense. But the tropical cyclone debate is that, yes, they're probably becoming more intense, but they might become less frequent because of other changes in the dynamics. And so that's also true for these things like hailstorms, that yes, there's more energy in these systems, but there's other changes that might impact that as well. So that's where we get far enough away from sort of these mean temperature changes that it's quite hard to know for sure. And so we really need a lot more research to truly understand that.
Thank you.
Thanks, Rachel. That was great. We could easily have a 5-hour discussion just on this stuff alone. But I think I'm going to have to flip it over to Dipika as our second speaker. Dipika, take it away.
Thank you very much. And I would just like to ask for a quick check as well for sound and slides, please. You can see them, you can hear me?
Looks good.
Absolutely, yep.
Thank you. So I would like to start with a land acknowledgement as well. So I'm talking to you from Toronto, the city of Toronto, and it's the traditional territory of many nations, including the Mississaugas of the Credit, the Anishinaabe, the Chippewa, the Haudenosaunee, and the Wendat peoples. And it's now home to many diverse First Nation, Inuit, and Métis peoples. So thank you so much for inviting me in, and I'm really pleased to be talking to you all today. I will skip over a couple of sections, but we may go through that again, depending on questions and interest from the group. But I'll talk to you from a reinsurer's perspective. This is quite biased from a Swiss Re perspective as well. But I'll talk to you in terms of how do we view climate change and the impact it has on our view of both modeling exposures, modeling risk, and how we price for things. So I'll try to give you some insights into that. And I'll start with in terms of how do we incorporate, we at large, not just Swiss Re, but how do we incorporate climate change into our modeling view? So that kind of opens the door in terms of how do we price for risks? And in terms of my role as an underwriter, I'm really looking at treaty. So I'm looking at full portfolios that we're taking on to our balance sheet from insurance companies. So very briefly, and I'll try to skip over this one, I won't spend too much time, but we do exposure rating and we do it should have said experience rating on the right side, sorry. The right side is experience. But exposure rating, what we do there is that we try to understand, well, what are the characteristics of those exposures that we're bringing in onto our balance sheet, and how would we rate for those? So that first section, modeling by peril, that's really where majority of the climate change science comes into play. So we're looking at probabilistic models. We're trying to look forward. It's backed on the good science that Rachel, she just walked us through. And these kind of like exposure models, the peril models, they tend to be fairly sticky. We don't update them on a yearly basis. We update them every 5 or 10 years because there's quite a lot of data that sits behind them, and they're quite large undertakings. That's one way of doing exposure rating. The other one is to actually use less sophistication, so not to use probabilistic models. That really, we're forced to go down the regional tools side when we don't have strong probabilistic models, or we're in development, but we don't really have that high confidence in them. But we're trying to basically look at historical losses. We're trying to look at the information we have about the region. It could be how many people live there, what's going on the inflation side in terms of claims payment to anticipate that. How much is that insurance portfolio growing? And these kind of regional tools, they're updated at much more frequent tempo, simply because it has to. It's not as big a task as it is to update the peril models. These are Excel-based, or they can be more sophisticated than just using Excel, but they're smaller regional tools that updating certain indices does not really take very much time. For the distribution of the slides, I'll make sure that the heading is correct, but on experience rating, we basically look backwards. We're looking at history to inform us for our loss picks and in terms of how we're going to look at pricing a certain treaty. So moving forward, I'll then go into more of a Swiss Re biased view here. So we talk a lot about climate change, and if you're ever talking to a Swiss Re colleague of mine, we talk quite a lot about secondary perils. So I just want to do a little bit brief overview in terms of how does climate change look like, what do we mean by secondary and primary perils, and just kind of level set a little bit there. So on the left-hand side here of this slide, you can basically see what we deem to be primary perils. So by primary perils, we really mean things that we have good confidence in. So it could be, for instance, the BC quake model. It could be certain aspects of tropical cyclones. European windstorms is deemed to be a primary peril. Japanese earthquake, we have quite high confidence in. So these primary perils are what the industry, the insurance and the reinsurance industry, has high confidence in. I do want to just pause and just acknowledge Rachel's, one of her last slides in terms of all models are wrong. Absolutely. I just want to hone in on that. So BC quake, part of the reason why we have high confidence in it is that this is the best science. We've compiled it all. We model our portfolios on that basis. But when a BC quake happens, we're all going to be updating our models, because I'd be very surprised if any one single model is correct. They are all going to be wrong, and we'll be able to recalibrate our earthquake models after events. So we always get smarter post events is basically the conclusion there. But that's the primary peril space. On the secondary peril side, really, I probably should have put in a moniker to say that secondary perils are what we have little or no confidence in. There's too much that we don't understand. So those are the perils we're deeming to be secondary. So there's one bucket that says it could be secondary effect of a primary peril. So it could be liquefaction after an earthquake or during an earthquake. It could be fire following an earthquake. It could be the storm surge that follows the tropical cyclones that Rachel mentioned. But basically, these are aspects of the primary perils that we actually don't understand very well. The larger bucket, the larger component of the secondary perils, though, are the independent secondary perils. So there are just simply things like Jeff's question in the comments. It's convective storms, thunderstorms, tornado formation, wildfire, droughts, snow and ice storms. There are certain aspects of that we don't understand so well. So there's a lack of robust and efficient tools, as I've written here. And we basically have a significant knowledge gap. We're not quite at that point where we understand these independent perils enough that we can have a certain level of confidence, excuse me, in those models. One second. So that's basically where we see secondary perils. So the question then comes, does climate change, fit into this? And here, in terms of if we look at the loss experience that we've had on the insurance and the reinsurance side, we know that we've seen increase in losses. Some of that increase is coming from climate change, and some of that is simply coming from the environment that we live in. So within Swiss Re, there are certain aspects that we feel that we have higher confidence in, like We see an increase in the heat waves. We see the increase in sea levels, so certain storm surges are increasing. We see that increase in precipitation. But then there are other aspects that we have lower confidence in. So by lower confidence, it's not to say that climate change does not impact tornado formation, hail formation, but we have low confidence in terms of being able to understand it, to say that, well, it is because of climate change that we're now seeing a tornado in Barrie. We're lacking that kind of confidence. But absolutely, climate change as such, Swiss Re has been drumming the drum since the late 70s that climate change is an issue, and it's a worldwide peril that we are all very concerned about and that we are not prepared enough for. But when we're then talking about those increases in losses that we're seeing within the industry, it's also due to the fact that we have more accumulation of people, more accumulation of exposures in smaller areas. So that urbanization rate is something that is contributing factor to the increase in losses. The inflationary pressures that we're all seeing at the moment, we have been seeing for the past few years, that is also part of the reason why we have an increase in losses. We see, aging infrastructure. So whether it's the sewage system, whether it's the way that we live in terms of concrete building versus green buffer zones within cities, that infrastructure has quite a big impact as well. And then sprinkle on top a pandemic, some labor shortage, supply chain issues that are global of nature, sprinkle in a little war. These are going to have quite devastating impact in terms of that increase in loss view. So after that, I'll then basically go into that loss view in terms of what are we seeing globally. And when I talk about, when I talk about that increase in losses, what exactly are we talking about and where does climate change come in there? So this is probably a graph that's quite familiar to a lot of us on this call. We've basically, this increase in losses is what this picture is showing. So it's showing natural catastrophe losses from a period starting from 1991, and it's only been split up here between earthquakes and weather events. So not much of a delineation here, but we can see that where it comes to the earthquake losses, they happen once in a while, but they're quite severe when they happen. And another trend we can see in this photo is the fact that the weather-driven events, they are increasing both in terms of severity, but there also seems to be much more variability that's going on as opposed in the latter period, as opposed to the first part of this period. And if we dive into a little bit further into that primary versus secondary view, it becomes a little bit more interesting. We still have the primary perils of earthquake being there, but we're also now picking out certain aspects of tropical cyclones, winter storms, Europe, things of that nature. So we have that squared off. And basically anything that's blue, purple, gray in nature here is where we have the secondary perils view. These are the perils that we feel less confidence in. So we are concerned whether or not we are appropriately costing for them, appropriately anticipating what kind of a loss impact they will have for us into this year, next year, 5 years from now. So secondary perils are increasingly grabbing the headlines. Then I do want to go into very quickly where we see specific impact on peril by peril. Because one thing I skipped on that one first slide is that the modeling that we have available on the CAT side for us in the insurance and the reinsurance industry is peril by peril focused. We're not looking to price for climate change at large or charge even for weather at large. We like to do rating peril by peril. So maybe I'll just ask for your focus at the bottom of the slide first. So basically where we see consensus within Swiss Re is that we can see there is an increase in climate change. The temperatures are increasing. And what we're seeing in that increased temperature is basically we're seeing more water retention in the atmosphere. That science seems quite conclusive. And then what is that impact when it comes to our view on specific perils? So when it comes on the flood side, when in terms of fluvial flood, like floods bursting there by the seams, we can see that there is both an increase in flash flooding in terms of a lot of precipitation, whether it's rain, whether it's snow and snow melt, including very gradual that, there could be a lot of rainfall at the top of the river, and as the river flows through, there's this gradual expansion of flooding. So that's one of the things that we're seeing. Increased participation, both on a gradual as well as a flash flood basis. Pluvial then we're talking about cloudbursts. We're talking about rain simply falling from the sky. So we're seeing more precipitation, more intense rainfall. And on the storm surge side, in terms of that increase in wind, with the sea level rise, we do see much more storm surge. So not only are we seeing bigger waves, but alongside the bigger waves, we're seeing a bigger impact on the ground. So the land is being covered by more storm surge than it has been in the past with that level, with that increase in the sea level. On the pure temperature side, again, we're also seeing that higher average temperatures, those higher extremes that Rachel mentioned, we can see that they're producing both stronger as well as more longer droughts. So we can also see that in terms of the jet streams and how they're moving. So we both have, the perpetual, I shouldn't say perpetual, I should say the longer lasting heat dome situation, where it can be quite a stable fixture, particularly what we've seen in Western Canada last year. And it just seems to be lasting longer. The flip side of that is even actually, not just for the wildfire, but if we talk about those changes in the jet stream, we can also have the Arctic, the name now escapes me, but the deep freeze situation also seems to last much longer with that jet stream, that lip that kind of covers us. Where again, a good example is last year's Texas freeze example that comes from that change in jet stream. Then on the right-hand side, that's basically where we're coming into the less confidence. So these are the secondary perils in terms of winter storms. So what we do see is the more extreme. So we can see these more extreme temperatures. So we're a little bit concerned in terms of whether we're going to see more winters that have freeze and thaw. So that kind of like intermediate, like going into and out of winter during the winter months. So we're a little bit concerned about that. We can see that. But again, we don't have that strong modeling capability at the moment when it comes to winter storm. So we basically see more extremes and we see that increased precipitation. But in terms of being able to predict how those extremes are going to play out, whether we're going to see 3, 4, 0 thaw and refreeze situations, we're not able to do that at the moment. And then to Jeff's point earlier, in terms of convective storms, we don't have that strong scientific link. We don't understand enough about the convective storm in terms of the frequency, the severity, impact from climate change. And when it comes to convective storm, this is a peril that is quite notoriously difficult to model because things can just be so localized, right? So whether we're going to have tennis-sized hail formation versus dime-sized, that could just change from one side of the street to the other side. That's how localized it is. So our predictive capabilities on convective storm has a lot to be asked for still. We need to increase our understanding there. So I would say for wildfire, winter storm, and convective storm, those are the secondary perils that we have less certainty of. So we're using more of those regionalized tools that I spoke about on the first page. And when it comes to flood, that's something that is becoming better modeled. It's more so fitting within the primary peril side than the secondary peril. And there's stronger links from the climate change science into what the impact is on the flooding, as opposed to, for instance, convective storm. And then I'd like to also just briefly touch on the other aspects of secondary perils, other aspects of climate change that are impacting us in Canada that we also have less understanding of, but I'm sure that our understanding is only going to increase in the future. And one of those is landslides. So for instance, last year in BC, the fact that we had that pronounced drought situation, you're seeing vegetation that is shriveling. Of course, a lot of it has been burned down as well. So there is a lack of water retention within the soil, actually. So then when you have prolonged rain events that follow that after a few months, you do see this intensity of landslides. It hasn't produced very large insured losses for the time being, but landslides is definitely something that's on our radar that we're going to look at more in Canada. And then another risk we see from the quite intense thawing of the permafrost in Canada is that we could see an increase, not an increase, but just I guess we could see the preponderance of peat fires actually happening. So peat is this very flammable material that sits either above, well, just at the ground level or below ground. And that can ignite very fast from such things as lightning, of course, mainly from natural sources. And once that catches fire, these peat fires underground can burn for decades. There's some live examples of that both in Russia as well as Indonesia. So peat fires is one of those things that it's another secondary peril, another consequence of the heating climate that we're concerned about and that we do not have modeling capabilities for currently. So the last two slides I have are just very quickly in terms of what we do well, what we don't do so well within the insurance and the reinsurance industry. I think we're pretty well poised in terms of decreasing the protection gap, in terms of where our models are good or better or worse. We do have a better understanding today than we did 5-10 years ago in terms of how can we close the protection gap, how can we make sure that more people are insured so they can bounce back faster after events take place. One of the negatives that I see at the moment is that there's so big variability when it comes to the secondary perils view. So if you talk about wildfire, if you're asking a Swiss Re underwriter versus a Travelers underwriter versus an Aviva underwriter versus a Munich Re underwriter, everybody's going to have a pretty different guess as to what is going to be that expected loss for a wildfire for next year. And that variability is quite concerning, that we don't have that consistency of view as we do for so many other NatCat perils. And then I'm quite heartened by the fact that there is quite a lot of resource deployment. So Rachel mentioned this all. There's a lot of good research that's being done at the moment to increase our understanding of climate change, its impact on us. So that is going well in the right direction. And very briefly, not to linger too long, there's a lot going on. I know that Matthew will talk a little bit more in terms of what is being done between the insurance reinsurance industry as well as the government and other stakeholders in terms of improving the resiliency for us here in Canada when it comes to flood. Also for earthquake, there's a file that's moving forward very well. I would also urge us to think about green infrastructure. How can we bring in more buffer zones within Canada to make us more resilient for the weather that we're actually seeing and experiencing? And how can we, on the insurance and the reinsurance side, actually help bring that about? And how can we bring in more green infrastructure? How can we enable and facilitate that? And then I think that we have a lot to do in terms of risk mitigation when it comes to building back better. Something burns down, there's hail impacting us. We need to have more programs like the city of Calgary has had in terms of then improving the roof quality, making sure that we're actually actively pouring in more money to improve the way that we live. Let's not live in stick houses and see that wash down year after year. So there's a lot I think we can do on the insurance and the reinsurance side in terms of improving the risk that we have from climate change in Canada. And there's a lot of good initiatives already going on. So with that, I'll thank everyone and open it up for quick questions if there is anyone for me. Otherwise, I'll pass on to Matthew.
Thanks, Dipika. I think we'll flip right over to Matthew, and then we'll get into the Q&A. Thanks.
Okay, so is everything correct? So do you hear me well and do you see the presentation? Just put a thumbs up.
Looks and sounds good. You're good.
All right, great.
Go.
All right, thanks a lot. I'd like to thank the organizers of this webinar for giving us an opportunity to talk about climate change and climate risk modeling. So on my side, I will discuss more about the financial risk management of flooding in Canada. Well, the current context, the future, and how to, and also a discussion about how to integrate climate modeling, climate change modeling into our financial risk management from the insurance perspective mostly. So I will briefly talk about the current context on flood insurance in Canada, and then I'll move on discussing about flood risk modeling with under climate change, some of the pressures that the industry is facing, from reporting and regulatory standpoint, how to use statistical, actuarial, science models, and climate models to provide physical risk assessment under TCFD. I'll provide some examples of how to make it work in practice with research partnerships that I've done in the past. And also we'll discuss of the way forward in terms of financial risk management and what we need in the future to better prepare for flood risk and climate change in the country. All right, so flood insurance in Canada is a shared responsibility between the federal, provincial, and territorial governments. So if you're an homeowner at high risk of flooding and you suffer losses from a flood, you might be entitled to receive financial assistance from your province's disaster financial assistance program. If for a given province a flood is too important in terms of the amount of losses, so it's too catastrophic, then the disaster financial assistance arrangements from the federal government can support the provinces, not the disaster victims, but the provinces, by providing additional financial assistance. So this is done through a risk-sharing formula, which is agreed upon between the federal and the provinces. And basically, as the flood event gets more and more catastrophic from a financial standpoint, the federal government assumes a larger and larger share of the catastrophic losses. Before 2015 and 2016, there was no overland flood insurance offered on in the insurance market, and this is something that has changed after the Southern Alberta floods in 2013. So there was an increase in pressure coming from the federal government so that the insurance industry gets involved in selling overland flood insurance. So right now, this is much more common. This is sold as a water comprehensive package. So this is included. So overland flooding and sewer backup are packaged together in a single product and sold as an optional rider. And because this is optional and the premiums are risk adjusted, the take-up of such package remains relatively low in the country. So depending on the sources of data, the provinces, and obviously the level of risk, well, we're talking on average about 40 to 60%. But obviously for those who are at high risk of flooding, insurance is either not available, but when it is, obviously premiums are very high, or coverage it might be insufficient. So in order to tackle that issue of lack of insurance for those at high risk of flooding, that's why the federal government has put in place in early 2021 this task force on flood insurance and relocation. So this is basically a discussion with the federal, provinces, and territorial governments, municipalities, the insurance industry. And the overall goals of this task force is really to look into different options for low-cost insurance for those who are at high risk of flooding, and for those who are at the highest risk of flooding, investigate whether relocation might work. Okay, so a report is due. It's a matter of days or weeks before something will be released, at least publicly. And according to the Minister Bill Blair, he was talking about the launch of a program in 18 months. To be honest, that seems to be quite aggressive, but that's a political decision. We'll see what happens next. In all of these discussions related to flood insurance, they also occur in a context where there's a clear rising costs in either water-related damage or flooding in itself. So you probably heard the saying, water is the new fire by the IBC, basically means that water-related claims are greater than fire-related claims. So that includes sewer backup, and that claim was made probably around 2017, 2018, even before overland flood insurance was more popular in the market. According to the PBO, Parliamentary Budget Officer, claims made to the DFAA with respect to flooding have quadrupled over 40 years, and about 75 to 80% of those losses are due to flooding. Obviously, that increase in losses due to flooding, well, there is some signal coming from climate change, but obviously there's also urbanization, inflation, aging infrastructure that have all contributed to these rising costs. So urbanization, it's something we can tackle with respect to the governance of flood risk among the different levels of government. And climate change, well, there's a mix of tools that we can use. So mitigation, adaptation, obviously. And that's exactly what I'm going to talk next about the preparation of the governments and the industry with respect to climate change. So right now, there's a lot of pressure from investors and other stakeholders to better prepare for climate change and also to reduce the future impacts of climate change and obviously reduce greenhouse gas emissions. So pressures to decarbonize our investment portfolios and also pressures a lot by investors to disclose and stress test the impacts of climate change. So as of today, disclosing impacts of climate change, it's mostly a voluntary initiative. And it's mostly qualitative as well. But we do expect in the future that this is going to become mandatory, and not just trying to find out and build a qualitative assessment, but also on a quantitative aspect as well. So to bring in numbers and to bring in the potential losses in the future due to climate change on a given organization. So thanks to the work of the TCFD, the Task Force on Climate-Related Financial Disclosures, they have provided a set of guidelines to better help governments and organizations to disclose, for example, the impacts of climate change, and also to better organize governance of organizations around climate-related issues. So there are three typical risks that are identified. I'm going to focus more on physical risk, which is basically the financial impacts of a potential increase in frequency and severity of climate extremes or climate-related losses. So how do we tackle this physical risk assessment, for example, for an insurance company? Well, in fact, what is needed here by those reporting and stress test scenarios, it's to look at the impact of various warming scenarios on the financial results. So what would be the impact of a +2 degrees increase in temperature on flood losses for an insurance company that sells flood insurance, for example? So that needs us to look again at the catastrophe and flood modeling process, especially on the hazard side, and try to determine what would be the impact of climate change on different horizons and for different RCP scenarios or greenhouse gas emissions concentration scenarios. So here we really need the expertise and all of the work coming from climate science, climate scientists, sitting on the shoulders of giants. That's very important here. And that's what we did. So we fully integrate the outputs of regional climate models. So basically, we need to have this top-down view of a catastrophe or a flood or flooding here in this case. So how do greenhouse gas concentration scenarios impact ultimately the dynamics of precipitations and temperatures locally and all across the portfolio? So this is really challenging because if you're a Canadian insurer, you probably have exposures across all of the provinces. So you need to have this representation of the financial impacts of an increase, of a potential increase in flood risk all across your portfolio. So this is quite challenging, and that's why we have undertaken in the past with the private and the public sectors different partnerships to tackle this issue. So provide here first proof of concept of how this can be done. And this is work with Uranos that we have done. We finished that over 2018, 2019, I guess. So here, this is really the ideal case, okay? We were working also with the Ministry of Environment. So we were working with engineers, hydraulic engineers that provided us like tons of flood maps over a small portion of the Chaudière River in Quebec, in Sainte Marie. So we had all of these flood scenarios under RCP 4.5, 8.5 over 2 different horizons. So that gave us a sense of how much potential losses would increase over Sainte Marie over different time horizons. And that also helped the municipality of Sainte Marie to better plan ahead in terms of relocation of many properties that were at the highest risk of flooding. This is, of course, an ideal modeling when you have like these sets of maps provided by hydraulic engineers. But imagine if you're a Canadian insurer, like the cooperators with whom I worked with over the last couple of years, and I'm still working with them in terms of research partnerships. So imagine you have a large portfolio and you need to assess the impacts of climate change all across of your portfolio, across provinces, everywhere. So it is extremely difficult to do that kind of work, very precise work with like aircraft models or hydraulic models at high resolution. So this is really difficult. So instead here, what we did, we tried to simplify that hydrologic and hydraulic process with a kind of a hybrid modeling, so both statistical and physical, but really it's just to have a broad overview of how much flood risk could increase over a large portfolio. So we have designed this North American model at the resolution of our regional climate model, so 10 or 25 kilometers resolution. This model is focused on heavy rain induced flooding. So here we have like the differences in flooding probability over each grid cell over Canada and US. So this has shown to work. This is something that we have done, and we have also worked on the riverine aspect as well on flooding with a similar approach. So this hybrid modeling where we integrate outputs from the Cordex North American ensemble. This is really like there's a lot of work, there's a lot of data involved in order to include those climate models. So here, this was really a proof of concept that worked with the cooperators. So based on the experience I had by working with the private and public sectors, how can we better prepare ourselves here in Canada against the adverse effects of climate change on flood risk? So there are multiple aspects that we need to look at to better prepare ourselves. So right now, there are significant efforts that are being deployed to update flood maps. Okay, so in terms of flood mapping, it is extremely important to update those flood maps because many of them, they date from the 80s. I mean, I like the music from the 80s for sure, but the flood maps from the 80s, we need to update them, of course, for sure. So those are a list of desired features of flood risk modeling that we do like for our future flood maps. We want Canada-wide availability. We want them to be dynamic. Dynamic because, well, the occupation of land changes over time. We might introduce flood defenses. So that changes the dynamic of flood risk. We need to have that easily and frequently updated. Obviously, we need something that accounts for different concentration scenarios, so different RCPs. You need something with a standardized methodology, high resolution, and I know those are my grocery list of things that I want, but it won't be that easy to get all of them because, well, first of all, even the inputs for producing those flood maps are missing in the country. So we're talking about high resolution DTM, digital terrain model, whose coverage is not even complete in many urban areas, just like in the Ottawa region. We might be talking about rain gauges, measurement of discharge in many areas. The coverage is scarce. We don't have enough data. Also, flood mapping is a responsibility of municipalities. So even if it's supported by federal, provincial, and territorial governments, we know that we know that there's going to be a lack of coordination and maybe resources on the part of municipalities to tackle of these challenges with respect to flood mapping under climate change. So there seems to be like, well, it will almost be impossible to have a standardized methodology all across the country. And this has a lot of consequences for financial risk management. So imagine you're, again, Canadian insurer. You want to know more about your flood risk all across the country. Well, you have to collect yourself, reconcile the flood hazard map information, and also understand all of the methodology that has been applied in different municipalities or provinces. So it's a really huge task. And that's also why there's also a heavy reliance on international CAT modeling, CAT models provided by these international vendors. Even if we do have the expertise here in the country, probably a better expertise even then to understand what's going on. For example, with the climate in Quebec or in Ontario, that is different than in BC. So the flood dynamics are different a lot across provinces. Also, flood maps are great for pricing, underwriting, but for capital risk management, systemic risk, assessment of reinsurance, solvency analysis, we need more than that. We need probabilistic event sets, and that's something that is often lacking also in the country. We need more data in terms of exposure. So insurers can collect this information at the underwriting stage, but from a research perspective, I can tell you this is something that is really difficult to get. Value of the properties, property characteristics, those will influence a lot the dynamics of financial losses due to flooding. Vulnerability information. Can we have our own Canadian damage curves or our own provincial damage curves? There's some work that has been undertaken by Natural Resources Canada, but we do need to do more, okay? There's a lot of data available within the provinces with respect to flood death and claim amounts, but those are confidential information that are within the provinces because of their provincial DFA programs. I talked about residential properties. What about infrastructure? There's also a deficit of knowledge about that too. So overall, if we want to better prepare against the adverse effects of climate change and build up like an appropriate financial risk management plan for the country, well, the saying goes by like that. What we cannot quantify, we cannot manage appropriately. So we do need the required input to be able to better quantify the risk in the future. To better prepare Canada to flood risk and climate change on top of that, well, yes, we need to tackle our flood mapping issues, but we also need to tackle our governance of flood risk, okay? So right now, the responsibility of land use planning is in the hand of municipalities, whereas most of the financial risk is borne by FPT governments. So there's this moral hazard. Federal government should also be focusing a bit more on, well, not a bit more, much more on risk reduction in the future rather than recovery. And also we need to balance mitigation and adaptation. It's extremely important to tackle the reduction of greenhouse gas emissions, but we also need to look at adaptation, risk reduction. So in terms of flooding, we're talking about floodproofing, relocation, and providing appropriate insurance for those who are at low and medium risk. For the industry, obviously on the asset side, decarbonize investments. This is also an important gesture by the insurance industry to undertake. In terms of adaptation, here's a list of what we can do. That was also discussed in the previous discussion. And I will finish up with governance within the organization. Talking and taking decisions with respect to climate change needs also some change in the governance within an insurance company, for example. We're talking about having people with that specialized expertise. We're talking about creating a department in climate and sustainability. It's not just a matter of bringing numbers for the regulators or the accounting organizations. It's also in terms of strategic decision making. It connects with marketing. It connects with finance and actuarial. And to do that, well, there's a need to train people, recruit experts, and also update the computer infrastructure, because working with the climate models, well, there's a lot of data. Okay, so that's it for my presentation. Thanks a lot. If you want to know more about the work we have undertaken with research partners, if you want to know more about the technical details, if you want papers, another presentation, just don't hesitate to write me an email. Thank you very much.
Mathieu, thank you very much. That was great. And thanks also to Rachel and Dipika. We just have a few minutes for questions. Before I get into some of the questions that I've prepared for our presenters, Danica, there was a question in the chat box. Would you be able to share that with, I believe, Rachel?
Yes. So the question is from Paul, and the question is, what type of aerosols are masking greenhouse gases?
Yeah, that's a great question. And I will point out I am not an aerosol expert. And so there's a lot of, I realize I'm saying this a lot, there's a lot of complicated factors. And so there's direct aerosol effects. And so aerosols like sulfur dioxide will reflect incoming solar radiation, and that cools the planet. Other aerosols such as black carbon, so sort of soot that gets up into the aerosol, actually absorbs that solar radiation, but it absorbs it in the atmosphere, and so we're warming the atmosphere, but that's sort of shadowing the surface, and so that's cooling some of the surface. But there are also what's known as indirect aerosol effects, and so all of these aerosols like dust and sea salt and these sulfur dioxides can act to change clouds. And so when you have aerosols in the atmosphere, and so we can see this in ship tracks, we can see this in airplane contrails. It's actually mostly the aerosols that are coming out of these that are causing water vapor to condense onto the aerosols, and so creating clouds. And then obviously clouds are white, they're reflecting solar radiation, so that's also impacting the radiative balance and can cool the atmosphere. But yeah, some aerosols, right, have more of an indirect effect, some aerosols have more of a direct effect, and so all of these impact the climate in slightly different ways. And so we're still trying to work out exactly how each type of aerosol impacts the clouds, how it impacts the radiation. But I know that sulfur dioxide and black carbon are some of the biggest ones.
Great, thank you for that. Dipika, I think we start with a question for yourself. So I think some say that climate change is not and will not be a big issue for insurers and reinsurers because the contract only spans 12 months, right? We hear this all the time. Some people argue that modifications can be made to contract wordings or the pricing, or the carrier can even walk away from that business if it gets unprofitable. It's kind of a simplistic view. Why do you think that this is not giving us the full picture? Why is it more than just, you know, all the contracts, 12 months, this is not a big problem? What are your thoughts on that?
I have many thoughts on that. Predominantly, I'll break it down to two components. One is that when we're looking at that loss graph, like losses are increasing. Where they're increasing from, predominantly from the weather perils. Where are most of those weather perils coming from? There's a direct link for climate change for many of them. So I would say that if you're having a 12-month contract, climate change has a direct impact in terms of what the loss pick is going to be. So when I do an expected loss guess for the next upcoming year for that 12-month period, it's based to a large extent on historical view, and we're trying to bring more of a forward-looking view into place now. So I would argue that within the industry, we're doing a poor job. Like, we need to be better. We need to incorporate more of a forward-looking view. But even if we look back, so let's just look back at 2021, 2020, 2019. If I don't have to look very far into the past to actually have a pretty decent view of what my loss pick is going to be for the future. Now, I would personally not go back to 1991. I don't think that those events that occurred are going to be very indicative of what's going to happen in 2022 or 23. But basically, the first point is that climate change has already impacted the losses we're seeing, so it's already part of my loss pick as an underwriter. The other issue is that when it comes to these 12-month contracts, there is a dynamic interplay in place. So in terms of that pricing component, it becomes quite important, Glenn, that when we're looking at, you know, losses that the industry insurers or reinsurers have paid for the hail losses of 2020 and 2021, there is a sense of well, there's a question, I should say, in terms of have we charged adequately for that? So that pricing adequacy is the other issue. When it comes to a 12-month contract, we're able to actually incorporate the most recent learning, whether it's from events or whether it's from the science, into our loss picks. So that 12-month cadence that we have in terms of renewals is something that's quite healthy, I would argue, for the sustainability side in terms of making sure that insurance is available. And so that's my answers in 2 buckets, but I do want to talk about the consequences thereof, because what we're seeing is that the impact we're seeing in terms of the variability of the climate, like Matthew was saying, there's certain areas with Canada where it's such a high risk zone in terms of flooding that there is no insurance that's available. And that's becoming a problem where so in terms of the losses I see as a reinsurer, they're already netted out of where there is no insurance in place. So we are underestimating the impact that climate change already has. If we're only looking at insurance losses, we really should be looking at economic losses. And that was the protection gap mentioned that I had said before. So I'll leave it at that.
Right. Matthew, any comments on that, since you work so much with insurance?
Yeah, that's for sure an issue. I mean, at some point, if the insurers decide not to provide insurance for those who are at high risk, or as the losses increase over time, what happens is that it creates more and more of a coverage gap, insurance gap, for not only those who are known to be at high risk, but others as well. And what could also happen for the insurance industry is that it increases the reputational risk of the entire industry. So at some point, that's also why these discussions on how to tackle flood risk and those who are at high risk, there needs to be this discussion with all of the key stakeholders. Okay, so we all have a role in trying to reduce the impacts of flood risk, for sure. And I think there's room for all stakeholders to participate over that. So reputational risk, there's a concrete example over 2013 with the floods in Calgary. I mean, in theory, it was not supposed to be covered, but then there was this domino effect. One insurer started to pay for the flooding for the flooding losses. And then move on to other companies, because the companies were afraid there would be reputational risk for them. And there's also these strategic decisions that need to be taken by the company. So yes, contracts are short term, but at some point, in terms of risk management, in terms of the positioning of a company and its reputation, it has to be done over a much longer term. So these decisions are taken really in advance. So that's why the time horizon, I mean, 100 years is too much, but it's also 1 decade, 2 decades. What we did, it's maybe over 40 years, but I mean, that's enough to have a broad overview of where this is going for an industry or for a company.
Right. Thank you. Rachel, BC was in the crosshairs last year, heat dome, heat wave, wildfires, and atmospheric river later in the year. It was certainly BC's turn last year, where it's often Alberta or Ontario's turn. What does the science say about how climate change is going to continue to impact these atmospheric river events? I mean, I should note that BC got hit with 5 or 6 of these last year. It wasn't just the one in November. There were several. And at one point we had one in the West Coast and on the East Coast simultaneously. But what does the climate change science say about these events?
Yeah, that's a really interesting question. And again, it's one of these ones where there's a lot of uncertainty, unfortunately. And so we can go back to these 2 ideas of there's this thermodynamic aspect where we're increasing temperatures. So we're increasing the amount of water vapor that's in the atmosphere. And so we're just increasing the amount of water that these atmospheric river events can transport into whether it's the West Coast or whether it's the East Coast regions. And then there's the question of the dynamics and whether something is going to change with the dynamics. And Dipika sort of mentioned, the jet stream and whether these sort of circulation patterns on the jet stream are going to be changing, and that's still unfortunately very uncertain. And so I sort of said these sort of three pieces of, like, the physical understanding, the observations, and the models. And with these types of events, the physical understanding still needs more work because there are so many complicating factors in there. The observations, we don't have a long enough record to really understand how they have been changing. And the models tend to disagree in terms of, are we going to get more atmospheric rivers? Are they going to shift as the jet stream shifts? And so those bits are still uncertain, but we can always fall back on this sort of thermodynamic understanding that we are increasing the amount of water vapor in the atmosphere, which is going to increase the amount of water vapor transport in these atmospheric river events, which we've always had. They're not unusual. We've just sort of heard a lot more about them when they cause these devastating flood events. But as they become more intense, that is just going to lead to more flooding. And so, yeah, there's more research that needs to be done on whether they're going to become sort of more frequent as well, or maybe less frequent. But the science, says that they will become more intense, unfortunately.
Is there any science about whether these have moved north more? I mean, I've been watching these for years, mostly hitting California and places like that. I don't really recall this kind of frequency in places like British Columbia. Am I imagining that? Or?
No, probably not. And so California, right, has had this like long-term drought that's causing their wildfires. And a lot of that is because of this northward shift, that these storms that would hit into them and give them some of their precipitation are just too far north. And so not going into that part of the coast. The question is whether this is part of a longer term, we say low frequency, so sort of decadal or longer timescales, just natural variability that the climate does do this. And so there are plenty of circulation patterns in the Pacific that slowly change ocean temperatures and always have done. And so this is the bit that's a bit uncertain, is knowing whether this is, right, a thing that's here to stay and this is a forced trend because of climate change, or is this just part of the natural climate? And in sort of 10 years or so, those atmospheric rivers, that jet will shift back south again. And so these are questions that we're still, right, as scientists, really trying to understand and get more definitive answers on.
Right. Thank you.
Hello, Glenn. There's a question in the chat.
Right.
All right.
Go ahead.
Okay. The question is from Horace, and without credible models currently available in Canada that could quantify secondary perils at the portfolio level, what are the alternatives that companies could use to measure these?
I'd be happy to take a first stab at that. So thanks for the question, Horace. I would say that there are actually a lot of things, if you just look at the past, that we haven't had good models for, but we've still been able to underwrite. So flood is probably a good example that Matthew mentioned. So 2013 happens, massive floods in Toronto and Calgary. The industry after that really took a hard look at itself and said, okay, let's provide flood coverage. Let's provide water coverage at large. And that was being done without a flood model. So if we look back 10 years ago, there was no flood model for all of Canada. And so I actually moved to Canada in 2013 in September after the floods. And I remember the conversation in the market was all about, oh my gosh, Canada is such a large country. There's so much water. How are we ever going to be able to model for flood? And fast forward 5-6 years, you start seeing the emergence of flood models. So I would say that sadly, we're a little bit, we learn by hard knocks in life. And this is another case where, we see atmospheric river events, we see devastating hail events in Calgary. We learn from these things collectively. So even when there is no model, so first of all, I'm hopeful that we will have more modeled view on these, but even without models, we can still look at aggregation. And as an insurance company, we may be saying, well, let's just draw circles around, well, there's a certain concentration. I don't want a bigger or a redder hotspot than a certain density when it comes to my aggregations, and look at that. And then there are interlaying factors as well. So you may not only want to look at the exposure footprint that you have, but you may also want to look at what the characteristics of that city are. So for instance, if you're providing wildfire coverage, which most insurance policies are and should do, if you're looking at a place like Fort McMurray, there's one road in, one road out. Maybe you would want to draw a smaller circle over that kind of an area. But where there are multiple roads going in and out of that town, that area, maybe you're more comfortable with a broader circle because you know that there'll be much more firefighting capabilities available. And also just from a governmental standpoint, there'll be less loss of life, less loss of critical infrastructure in those kind of situations. So all of that to say is that we can use, we can have a situation with no models being available, but we can still apply underwriting thoughts and portfolio steering aspects to that, even without a model, I'd say.
Thank you. And I have one more question for Rachel from Keith. Any views on removal of CO2 from the atmosphere?
Yeah, great question. I do have views. I think that's the only version of sort of geoengineering, and so this is a part of this big geoengineering question of, well, we're changing the climate by adding greenhouse gases, so perhaps we should change it by some other way to kind of counter this out. That's the only one that I consider is a viable and potentially sensible option. There are other ones, such as putting sulfur dioxide into the high atmosphere to reflect sunlight, which is just going to cause climate change in a different way. And so in another way that we don't understand. So that seems not a great choice for me. I don't know enough about sort of the science in terms of how fast this is progressing. And so that's the thing in terms of the question of how much can we take out of the atmosphere and store securely somewhere where it's not sort of under some rock formation that if there's an earthquake, it's all suddenly going to come back out into the atmosphere in one go. And so it is something I think we should be researching and researching hard, because I am worried that the speed at which we are reducing our greenhouse gas emissions is not enough to avoid some of the I mean, we're already seeing the impacts of climate change. We don't need to see any more. And so I do agree that it sort of has to be a multiple pronged approach, but we shouldn't have this as a, oh, well, we don't need to reduce our greenhouse gas emissions because we can just take it out and store it somewhere. The science and that is not solid enough yet to count on that as an option. But I do think it's something we should continue to research and try to make an option so that we can, we should do both as much as we can to reduce these impacts as much as we can.
Great. Thank you. We're running out of time. We're on borrowed time right now. What I'm going to do just really quickly, Matthew, I want to kind of take that question that Dipika just had about secondary perils and lack of models and kind of flip it over to a flood context. We have problems in Canada with flood mapping. We have problems with rain gauge network not being dense enough. We have issues with not having our own damage curves. How do we get beyond that? How do we do a good job at understanding the flood peril given these gaps?
Wow. No, that's a very good question. Well, obviously, the easy solution would be to invest more in terms of acquiring locally the data, so with the rain gauges and the stations. But until this is done and the flood maps are updated, I think, and that's also what I did on the research side, is try to develop alternative approaches to get a better approximation, for example, of how flood risk can evolve over the future. But to be honest, I'd prefer that we refine our current understanding of flood risk with more reliable data than these kind of approximations. But without appropriate data, and at some point you have to take a decision in terms of financial risk management or for an insurance company, well, you use approximations, you do the best you can. So there are techniques to interpolate flood risk in one river if it's similar enough than in another one that has better coverage in terms of stations and measures, but I mean, it's not going to be perfect. So I have not more. I don't have anything smarter to say than that.
That's pretty smart. Well, thank you very much. Listen, I can go on for a couple more hours easily. I have enough material in front of me to do that. We're having a great discussion here. I'm almost thinking that maybe we should have a coup and take this over from Ian and go on for a few more hours, but I can't do that. Thank you all. Excellent conversation. And Ian, I'm going to flip it back over to you.
Thank you very much, Glenn. That is probably a very good point to stop discussion, recognizing and honoring people's time commitments. So thanks very much, everybody on the panel, for being part of this. Glenn McGillivray from the Institute for Catastrophic Loss Reduction, and Rachel White from the University of British Columbia, Dipika Deol from Swiss Re, and Mathieu Boudreault from the Université du Québec à Montréal I wanted to ask Matthew, I was in Montreal yesterday and I went to St. Viateur Bagel and Fairmont Bagels, so I wanted to put you on the spot to ask you which was your favorite. Didn't get a chance to do that, so I'll leave that another time. Looking ahead, everyone, we have Danika's just going to post it up here. 2 forum meetings and 1 emerging risk webinar to close out the year. So we have a forum meeting taking place on September 15th. We're going to hear from the CEO about regulatory risk. We're going to talk about inflation risk and then also human resources and talent management. We had discussed that in the past, and we're going to revisit that with post-COVID to see how that has affected demand for young people entering the industry and retaining staff. November, date to be decided for the final Risk Officers Forum meeting of the year. You're going to hear about the upshot of our strategic planning conference that's taking place on June 9th. We are going to have our board chair in to talk about that. We're also going to talk about class action and supply chain risks. And the final emerging risks webinar of the year is taking place on Thursday, October 20, and we're looking at privacy. And so you're going to get tomorrow a copy of a satisfaction survey. So we thank you in advance for completing that, because your questions or your ideas, thoughts, ideas for feedback on speakers and topics for future certainly help to guide our broadcasts, and we welcome your ideas there. So thanks very much for joining us today. That concludes our broadcast. We look forward to having you join us for our next meeting. Again, the forum meeting is September 15th, 4 months from now. You have the summer off. I hope you enjoy it. In the meantime, stay safe, and we will see you soon. And thanks for tuning in today. Bye for now.